duality and defect CFTs.
Okay, thank you very much. Thanks for the invitation to this wonderful meeting. So let me not just write the title again, it's pretty long. But the goal of the two lectures will be mainly to discuss some recent results that myself and others have obtained in the context of computing correlation functions of local operator insertions inside Wilson loops, more precisely the AdS Wilson loop. And as I will explain tomorrow, these correlation functions are the structure of one-dimensional conformal field theory living on the Wilson line. And this correlation function, a strong coupling, can be computed basically by Witten diagrams on the AdS2 worksheet, which is dual to this Wilson lines. So this gives some version of AdS2 CFT1 duality, which is embedded inside the duality between n equal first degree and Wilson in AdS 5 But before we get there, so today the plan is to give introduction about relatively old and well-known facts about Wilson loops and AdS CFT. So start from kind of almost the beginning. So let me just review something that was said already in many talks. So AdS CFT, the very general statement, the duality between some quantum gravity in AdS d plus 1, say, space, and some conformal field theory living at the boundary. Now, most of the talks so far have focused, I believe, on the correspondence at the level of mapping local operators on the conformal field theory and states in the quantum gravity. So let me just briefly recall. So the general dictionary says that single trace local operators on the CFT side have to get used to this, are dual to single particle state. Yes. So for example, a scalar operator of scaling dimension delta is dual to some bulk scalar field with mass given by the familiar relation. This is the radius of the AdS, and this is the mass of the bulk scalar. Other operators, like for example the stress tensor, are dual to so the stress tensor is dual to gravity. In general, conserved current are dual to some gauge fields, and we can compute correlation functions of local operators by Witten diagrams. So pictorially, for example, the correlation function of stress tensor, say 3-point function, according to the AdS dictionary, will be given by computing some Witten diagrams where the leading contribution will be a 3-level amplitude of this form, where this is the cubic coupling of the graviton. Then there can be loop corrections and so on. 4-point function will be a sum diagram of this kind. Okay, and in general, the conformal field theory here has some Lagrange. It's assumed to have some Lagrange expansion, and the 1/n expansion on the CFT side is dual to the perturbative expansion on the gravity side. This is some very general statements about how AdS CFT mapping works, but in all examples that we know, in which we know how this correspondence work, the examples that we know best, these conformal field theories are typically conformal gauge theories, and in gauge theory it's very natural to also study not just local operators, but also non-local operators. There are many non-local operators that are natural in gauge theories. So the one that I will be focused on gauge theories We also have local operators. And for example, in any gauge theory, we can consider the Wilson loop operator given by the trace of the path ordered exponential. Where the integral is over a contour, so closed contour. So this is the space where the gauge theory is defined. We define a closed contour here. This can be thought as the phase factor associated with a heavy probe, in this case in the fundamental representation, going around this closed loop. Or equivalently, you can think of this as the creation at some point of the Q-bar pair, and then annihilation at a later point. Now, more generally, I can take this trace to be a trace in any representation, and then correspond to some particle transforming that representation, some probe transforming that representation. But so mostly the talk I will focus on the fundamental representation. So I will say something about higher representations if I have time. Okay, so this is an interesting observable in any gauge theory. It encodes important physical information about the theory. For example, it's well known that if we take a rectangular contour, say where this is the time direction, and this time extent is large T, and this space separation is L, then it's well known that the expectation value of the Wilson loop on this contour for large T goes like the exponential of minus T VL, where VL is the quark anti-quark potential. So you can think of this as the work line of a quark and an anti-quark, and this expectation value of this operator captures the quark anti-quark potential. So for example, in confining theories, VL, the potential goes like L, linear in the separation, and the expectation value of the Wilson loop as the area law, E times L, which is a familiar diagnostic of confinement. In conformal theories, like the one I will be discussing, specifically n equal 4 variables, this goes like some function of the coupling in general over n, which is like Coulomb-like behavior due to conformal symmetry. This is a V. So for example, as an exercise for students, you can try to take just the simplest gauge theory, take Maxwell theory, abelian gauge theory, dimension. Compute the expectation value of the Wilson loop with this contour, which can be done exactly because the theory is abelian, and you can find, you can easily show that the potential that you obtain that way goes like E squared, where E is the charge divided by L. In more complicated non-abelian theories, if they are conformal, you get a similar behavior, but here you get some non-trivial function of the coupling constant. Okay. So what about the AdS picture? So how do we describe this kind of local operators on the AdS side? Well, so when we have a gauge theory on the boundary, the quantum gravitational theory in AdS is a string theory. There are strings, and we know that the endpoints of strings behave like charges, quark and anti-quark. So it's very natural to suggest that if we have a little look on a contour C at the boundary, so this is the boundary, and say this is the holographic direction, so let me call it Z. So here I have in mind the Poincare coordinates in AdS. Then it's very natural to propose that the dual would be some string worship ending on that curve at the boundary. String worship. And in the leading order strong coupling, the expectation value of this operator will be given by the exponential of the minus the area, essentially, of the string worship. Okay? This is just a general expectation. To be a little bit more precise about what we are actually computing via AdS CFT, let me just focus now on the specific example of n equal 4 superiors and be a little bit more precise about what is exactly the operator dual to this string ending on the contour. Let me focus now focus on duality between SUN and equal force ranges and T. The basic mapping of parameters between the two sides has been reviewed already, I think, in several talks. Let me just very briefly write it down here again. So on this side we have N, the rank of the gauge group, that maps here to the flux of the 1/1 quadratic form. Field strength is 5. Here with the coupling constant. That would be noted as G square M Mills, and the tooth coupling lambda, G square Mills over N. And the mapping of parameters is that the fundamental string tension T, which is often parameterized as 1/2 pi alpha prime. So this is what appears in front of the worship action for the fundamental string. So the action of the string, T like T 2. Okay, in polytope form, or equivalently, you can integrate out this metric and get an Ambugoto form, which is the determinant of the induced metric. Area plus fermions, so this is just the bosonic part for fermions. Okay, so T here is just what appears in front of the string action, and the mapping of this to the parameters of the gauge theory side. So if we multiply this by the radius, this maps to square root of lambda over 2 pi. And the string coupling constant, which is the coupling constant that weighs the genus expansion in string theory, that maps to lambda over 4 pi n. Some conventions, or equivalent, it essentially maps to G square units. Okay. So in the tooth limit of large n and lambda fixed, the 1/n expansion maps to the string loop expansion or genus expansion. And large lambda expansion is the sigma model perturbative expansion. So we have an expansions in powers of 1 over n, which is the expansion in genus, so worksheets with genus 0, genus 1, and so on. And at each genus, we have an expansions in powers, inverse powers of 1 over root lambda, which is the perturbative expansion in this sigma model. Okay. Right. So okay, we set up also the convention, then they're called there are 6 scalars and 4 genus, so these are all in the adjoint. Okay, so I will run from 1 to 6. So you've seen many different ways of writing these 6 scalars. Here I'm just using the notation where they are in the fundamental of the SO6, or in the vector representation of the SO6 symmetry. Okay, and so what is the well, it turns out that the most natural Wilson loop operator to study, the one for which the dual is most straightforward, is not the usual Wilson loop that I wrote before, but some modification of it, which also couples to the scalar fields. Okay, so this is sometimes it's called the Mandelstam Wilson loop. So this will be specified by choice of contour on space-time, and also a choice of some scalar couplings, and is defined as follows. Okay, so theta I is a 6-dimensional vector. In general, it can depend on the position along the loop, function of t. So x mu of t is a closed loop. And from now on, I will exclusively stay in Euclidean conventions. So I'm just working on R4. This is a loop on R4. And theta I is a unit 6 vector. So it parameterize in general a point or a curve on a phi sphere. Okay? So there are many ways to see why this is the natural operator to consider. So the fact that we have a scalar coupling here, one way to understand it is that we have, so in fact to be strict, we have fundamental strings that end on d-branes, but those are not just charged under, they don't just couple to the gauge field, they also couple to the scalars, which describe the transverse deformations of the brane. The fact that this coupling depends on a unit vector is also natural from the point of view of the duality to AdS phi process phi, because when we describe this minimal surface ending on the loop, we in general should also say not only what it does on the R4, but also what is the boundary behavior of that worksheet on the S5 directions. So these couplings will basically be related to the boundary behavior of the S5 coordinates of the worksheet. Okay. Another reason that this operator is nice and natural has to do with supersymmetry. To go through the explaining in detail all the supersymmetry transformations and notation and so on. I just want to give you a feeling of the structure. So the supersymmetry transformations in n equals 4 superior is take the following form in terms of some spinner, some constant spinner. Okay. These are gamma matrices in the 4 directions. These are gauginous, so that's a transformation of the gauge field, and the transformation of the scalars is this, where these are gamma matrices in the 6th direction corresponding to SC6R. So this structure can be understood in an easy way from the dimensional reduction, for example, of n-dimensional n equal 1 superior to this 4 dimensions, where it is combining to just the usual variation of the gauge field. And this is a 16 component spinner, which encodes the 16 Poincare supercharges of n equal 4 superior to this. Okay, so there are 16 supersymmetries, n equal 4. Okay, so what is the variation under supersymmetry of that operator? It takes the following form. Essentially, well, this thing will be inserted inside the Wilson loop trace, but it's proportional to this when you take the variation of the exponent. And the fact that this combination of gamma matrices has a particular structure with this a unit 6 vector implies that this thing squares to 0. So it can be used to define a projector, and at each point along the loop there is a solution to this being equal to 0 with there's an 8-dimensional solution. So at each point along the loop, this is a half BPS, where half BPS means that it represents half this. Okay. So this, in general, is usually said in the following words. So Wilson loop of this kind, well, the Wilson loop is locally supersymmetric. What that means is that you can, in general, for arbitrary contour and arbitrary theta, you can always find the solution point by point along the loop, because the projector depends on where you are along the loop. But still, this local supersymmetric property is enough to guarantee some special feature of this loop. For example, you can show that this implies that this is UV finite for any smooth loop. Okay.
For me,
yeah.
So the quantity which multiplies epsilon 0, is it the projector? Or it can be used to define a projector?
Yeah, so this squares to 0, so it can be used to define object.
Okay.
Okay. Any such operator for any choice of this curve and scalar coupling is locally supersymmetric in this sense, and this implies some nice UV properties. So there are never short distance singularities in this kind of operators for any choice of smooth contour. Okay, but in general, you can. So this implies local supersymmetry, but you can find special contours X and special couplings such that you actually have global supersymmetry for the whole with the same spin or epsilon for every point along the loop. Okay, so those particular special operators are called supersymmetric Wilson loops. So for special choices of this pair, you can have supersymmetric Wilson loops in the standard sense, not just the local sense, in the sense that they actually do preserve some fractional supersymmetries. And so I'll mainly focus on the simplest ones, which are the AdS ones, but if I have time, I will also mention the more general case of less supersymmetry. So the simplest such case is the AdS Wilson line. There are questions? Okay. So take basically static quark, just static, very massive quark sitting there. That means in the Wilson line picture, we just have an infinite straight line, word line extending the time direction. Okay? So that means that we take the contour to be just a straight line, say in the x0 direction. Okay? And take the coupling at I to just be a constant. So if theta is a constant, it just picks a point on the 5 sphere. You can take any choice. Take, for example, just this for convention. Just pick one of the scalars. So taking theta constant just means that this couples to particularly a combination of scalars. Take that by 6. So and so let me call this. Let me choose the parameterization of the loop such that this x0 just coincides with the loop parameter and all other coordinates are 0. So the Wilson loop I'm talking about here, this AdS straight line, is just this. Okay. So this is a simple special case of the more general operator, and it turns out that this operator is AdS. It preserves half of the supersymmetry. It actually preserves half of the superconformal supersymmetries. Let me write here. There's a simple way to encode both the Poincare and the superconformal supercharges into a single object. Where this epsilon 0 is what I had there. These are the 16 Poincare supercharges, and these are the 16 conformal supercharges. And then we can study the variation of this operator under both Poincare and superconformal, and find that this will go like I, comma 0 plus comma 6. Epsilon 0 plus E, comma 0, epsilon 1. So you can solve this being equal to 0 because, well, here you just have some constant matrix which squares to 0, and you have another constant matrix which squares to 0 acting on epsilon 1. So you have two equations on epsilon 0 and epsilon 1. So this preserves 8 Poincare supersymmetry plus 8 superconformal supersymmetry. So it's AdS. As you may expect, due to this operator being BPS, it has a trivial expectation value, so the expectation value does not depend on the coupling. It's not normalized. It's exactly equal to 1 for all couplings. As an exercise, you can check this explicitly, but perturbation theory, say to first order, you can see that this happens because of cancellations between the pH field and scalar propagators. So when you compute this in perturbation theory, you will compute the first diagram will be a diagram like this. These are 2 points along the loop, and this is the propagator of the combined I0 plus phi 6, and that propagator is 0 when it goes from, well, when it goes from a point on the line to point. Okay, so it's useful and interesting to summarize the symmetries preserved by this operator. So these are the fermionic symmetry, preserves 8 Qs and AdS. What are the bosonic symmetries? So there is obviously an SO5 R symmetry because this operator couples to, we pick one of the 6 scalars, and then we are free to rotate the remaining 5, so there is an SO5 R symmetry. Okay, so that symmetry is there. There is an SO3 for rotations on the 3 planes orthogonal to the line. In other words, this is the spherical symmetry around the static quark. That's SO3. And then, importantly, there is an SL2R symmetry, which is generated by, so this is the symmetry which gives this line invariant. So it's generated by translations along the SDR direction, dilatations, and the special conformal generator along the direction. Okay, so this is the subgroup of the, well, these and these are the subgroup of the conformal group, which is left invariant by this line. Okay, so this SL2R is the one-dimensional conformal group. And the fact that this operator preserves this one-dimensional conformal subgroup is another way of saying that this operator is an example of what is called a conformal defect. So a conformal defect in the general CFT is just some non-local operator which preserves some conformal subgroup of the conformal subgroup. Here we have a one-dimensional operator which preserves a one-dimensional conformal group. So this is a conformal defect. It's actually a super conformal defect because it also preserves supersymmetry. And as I will explain maybe more tomorrow, this implies that if you study, say, deformations of these operators, you can describe those deformations essentially by inserting certain operators inside this line, because if you deform the contour, for example, you will insert field strength inside, and you consider as more general deformations, you'll have in general some insertion of operators there. And then the correlation functions of those insertions are constrained by this one-dimensional conformal symmetry and their structure of a one-dimensional conformal field. Okay. And as we'll see in a bit, this is also manifest on the AdS side. It corresponds to the fact that the worship dual to this operator is an AdS2 geometry. So all these symmetries, this bosonic symmetry together with this supercharges, combine into some superconformal group, which is OSP4 star slash 4. This is just a superconformal group where the bosonic subgroup is SO4 star cross SP4, and SP4 is the same as SO5, and SO4 star, it just means some particular non-compact version of SO4, which is equivalent to SL2R plus SO3, where this is the same as SU2. So it's SO4 will be SU2 plus SU2. SO4 star is a non-compact version of that, which is basically SL2R plus SO2. So these are the symmetries of this operator, and this is one of the possible one-dimensional superconformal groups with 16 supercharges. Okay. Any questions? Yes.
Could you elaborate a little more about what the conformal defect is?
So it just needs some local operator which preserves a fraction of the conformal symmetries. So these operators can only be planar or spherical. In the case of one-dimensional operators, it can be lines or circles, because those are the geometries that can preserve this kind of symmetries. So that's what conformal defect means, just some local operator that preserves some conformal symmetry. Wilson lines give an explicit example of that, but there are other examples that you can construct from the theory. Okay. Any other questions? Okay. Now there is a very closely related operator, which turns out to be, in some sense, in a clear sense, more interesting, which is the AdS circular. So now we just take the contour to be a circle, say on a plane in R1, and the operator take the parameterization where tau goes from 0 to pi, be concrete. Okay, so it's the same operator, except that now instead of a line we have a circle. So this is clearly related to that operator because you can map a line to circle by conformal transformations in N4. So you can just do the conformal transformation. For example, you translate the line, then do an inversion, and then translate back if you want this settled at the origin state. Or you can do it another way by mapping the gauge theory from R4 to S4 by variable scaling, and then the line will be mapped to an equator of S4. So this is clearly related, and it preserves the same superconformal symmetries. Well, the same group. But the generators are realized slightly differently due to this map that you have to do. So now the 16 supercharges are 16 linear combinations of Poincaré and superconformal. So something like AdS. You can show this explicitly by writing down directly the transformation rules of this operator using the epsilon 0 and epsilon 1 schemers that I used before. Then you can see that the supersymmetry variation now doesn't decouple for epsilon 0 and epsilon 1, but you get some relation between epsilon 0 and epsilon 1. So there are solutions where you have linear combinations. QNS. Okay. And even though this operator is related by conformal transformation to this one, it happens that the expectation value is now non-trivial. It's a function of coupling and rank of the gauge group in general. The fact that it's non-trivial has to do with some subtle fact about the conformal transformation, because it maps a point at infinity to a point at finite distance, and then the boundary conditions of the fields in the two cases on that point are different, because for the line we impose that the fields stay k at infinity, but not for a point on the circle. So the whole difference should come from just this fact that the point at infinity is mapped to a point at finite distance, and basically this can be seen as some kind of conformal anomaly in the sense that well, it's not a conformal anomaly in the usual sense, but it's an anomaly in the sense that the expectation value doesn't map one-to-one, but becomes non-trivial to the contribution of a point. So this kind of argument suggests that it should be possible maybe to compute exactly this by some kind of matrix integral. That was the original argument of Drucker and Gross. As I'll review in a second, it later was proved systematically using localization.
So, Simone, the fact that you can map the open Wilson line to a closed Wilson line,
Yeah.
and does it mean that you can map a non-gauge invariant quantity to a gauge invariant quantity?
No, they are both, okay, so they're both gauge invariant.
The open is also...
Well, yes, well, you still have a, provided you impose that the field and the gauge transformation decay.
Okay, that's what we just did now.
That's
Yeah.
the whole origin of this difference, is that the boundary conditions are different.
They are different in R4, but if you add
Yeah.
a point at infinity, they are.
Right, but if you are on S4, then there are no straight lines. So then there are only circles. So if you want, if you don't like to talk about infinite straight lines, you can just start from the beginning from S4, and then you just have circular after the S corresponding loop, and there is no reason that it should have trivial expectation value. You can just compute it by localization directly on S4. Okay, but it's easy to see that this is not trivial just by doing perturbation theory. So in perturbation theory, let's compute the expectation value of this divided by 1/n. Then it starts like 1. This. Then this is the combined gauge field scalar propagator plus higher order corrections. And so on. There are general principal diagrams with interactions and so on. Okay, so this kind of contribution here, given by this double integral. And if you're interested in these calculations, you should try to derive this result down here. There's this, which just comes from the trace of the gauge group generators, which are attached. So this is the Wilson line, this is the circle, and there's a propagator. Tau1 to a propagator, sorry, to an operator at 1, 2. Say A, E. So A, I'm just writing the adjoint gauge field as this, and these are the generators, so A is that index. So this, it's a simple calculation using, say, Feynman gauge to see that this is equal to this, and there is here a coupling dependent factor which comes from the propagators. Okay, so this just comes from the gauge field propagator here, there. There is a next dot here, next dot there. That's just the usual denominator that we have in the Feynman gauge propagator, and that's just the scalar propagator contribution. Okay, if you do this on the circular geometry, then this whole thing is just a constant. Okay, it doesn't depend on the point, on Tau1 and Tau2. So this whole first correction is so 1, and that correction is plus lambda over 8.
Sorry,
That's not the dot. Yes.
maybe I am a little down.
Yeah.
So X1 and X2 are points on that circle, right?
Yeah, so
Why is X1 minus X2 constant? If I choose 2 points on a circle, the distance doesn't look constant to me. Maybe.
well, I've already chosen some parameterization here, right? Where X.
Can you get, for instance, a diagram where the 2 points are very close to each other?
No, so
Oh, sorry. So
I mean, there's cancellation in the numerator and the denominator.
also X1 and X2 mean.
Just take this, say, to be completely explicit. I'm thinking already here a parameterization like this, where this is
Yeah.
right, and this just means x1 is x at tau 1 and x2 is x at tau 2,
Yes.
right? Do the derivatives, do this dot product.
So can you have a diagram where the points? So have a look at the first Feynman diagram.
Here, yeah.
Yeah, and
It
maybe.
doesn't depend on where the 2 points are. See, you compute it for tau 1 and tau 2.
Yes.
It's always a constant. There's just a cancellation between numerator and denominator. So this is like 2 minus 2 x1 dot x2, and it happens that there's a cancellation. Well, not a, yeah, I mean cancellation of the tau dependence, so you just get a constant. Okay, so these propagators, these three propagators from a point on the loop to a point on the loop are always constant. So this immediately imply that if we just say focus on ladder diagrams, by ladder diagrams, sorry, missing an E. But by ladders I just mean propagators that don't involve interactions inside. So just propagators like diagrams like this, but not like this. Okay. Then it's clear that this will be given by some matrix model, because it just counts, it's just a problem of counting how many diagrams there are, and the propagators are constant. You just have to see what is the value of the propagator you get from here. If you fix that, you see that this can be written as an integral over some Hermitian n by n matrix, and of some insertion which is basic to the n, and an action which is this specific coefficient just comes in these conventions by looking at what this propagator is. This is easy to see if you just focus on ladders. Now the original conjecture of Ericsson, Semenoff, and Zaremba, and Drucker, and Gross was that this captures the whole thing, so the interactive diagrams don't contribute, and they check that to this order. Okay. But then later, Teston showed by localization that this is actually true, so I can remove these ladders. Let me now write the formula again. It's actually true by localization that indeed the expectation value of the circular loop is just given by that matrix integral. Okay?
Question.
Yes.
Is there a simple way to understand why it's traced into the end
Rather than?
rather than some other random thing, rather than just the Gaussian?
Well, the Gaussian is here, so the Gaussian just gives the propagators.
Yeah, but
This is the it's just this operator. It's just this operator because we're just considering. Without I, it's just the fact that if you compute this propagator, you just get whatever you get from here, and then you just build this so that the combinatorics of this just reproduces
Okay.
ladders.
okay, that makes sense.
Is there significant?
But this-
to the 2n.
But that's just, I mean, you can put 2m here, and then you have to change the.
Oh, no, I just like different, so.
Different representation.
This representation, you just change the tracing. So if you want this one look in different representation, you
Yeah,
can
that's that.
just
Yeah,
put the corresponding true polynomial corresponding, and then you get. But there is a more direct way through localization to see why that's the result.
Sorry,
I'm running
just a
terribly
silly question before. So if instead of the supersymmetric Wilson loop you were to compute an ordinary Wilson loop,
Yes.
you would get a divergence, right? When two things get near.
No, so that's what I mentioned earlier. I didn't prove it. But when you have that operator that in general here will have something like
So I want to put 0.
x dot theta.
I want to put 0 there because I am considering an ordinary Wilson
Ordinary.
loop.
Yes. Then in general you have divergences.
Right.
Except in the special case of straight line and circle where the divergences can just, well, you can only have some kind of power like divergences inherent. Okay. So I'm not going to review the localization, but just give an idea of what it is. For those who don't know. So, general idea schematically is the following. Suppose you have some operator O or some collection of operators such that it's closed under some fermionic symmetry. So QO is equal to 0. Yes. Then you want to compute, say, so O could be this Wilson loop, for example. And you want to compute the expectation value of this path integral. Now let me be schematic. I just write d5, but it would be a path integral where all the fields of n equal force pyramids in this case. And we all inserted there and e to the minus s minus. Okay. Now the idea of localization is that instead of computing this, you can deform this action by a q-exact term. So you add to it something like this with a suitably chosen v that you have to construct in a clever way so that things work nicely. And then if this is q, if you add this, it's easy to show that this does not depend on t. So ddt O is equal to 0 because ddt will bring down qv, and if O is q closed, you can write that as a q exact insertion in the path integral, q of v, and the path integral of a q exact thing will be, the expectation value of the q exact thing will be 0. Okay. So then you can take t going to infinity. And in this limit, the path integral should localize to just configurations where qb is equal to 0. Okay. So this whole path integral then collapses to an integral over this locus, qb equals 0, and there is also an extra factor coming from the one loop determinant around this locus, which is t-independent, so it has to be capped. Okay. So in this particular case, for the AdS Wilson loop, it just turns out that if you study this problem and you build Q and V appropriately, the path integral localizes on just the constant mode of one of the scalars, which is phi 6, the one which appears in the Wilson loop operator. So W is trace P 6. Okay. So in our case, the localization locus is just phi 6 equal constant, and everything else is 0. Okay. So the whole path integral of n equal force pyramids localizes to an integral over a constant admission matrix. Okay, the Wilson loop insertion localizes to the n. We call this constant matrix m, right? So that gives that insertion, which is the m. And the action with the m squared terms comes because we are working on S4 and we have some conformal coupling to the scalars, which is a quadratic potential. Yes?
Simone, it seems that from the argument, the choice of V is actually, it applies to QV0, so yes, whatever V is, but no.
Right, but in practice you construct a V which is nice. So it doesn't depend on what V is. You can get, sometimes you can get different representations of this exact result by choosing different supercharges and different V's. They may be non-trivially equal to each other. So this is,
So each time you have different subspaces, but by scanning the space of operator V,
yeah.
you don't scan it when you still
I mean, the result should not depend on
Yeah, no,
what
I
you
should.
choose. 5 minutes. Okay. Okay, so I'm going to skip quickly through this. So let me just write the result. Okay. So once you have this matrix model representation, it's easy to compute the exact result for the Wilson group. Okay, so for example, limit m. So what you can do is go to do the usual thing that you can do with matrix models. You can diagonalize m and write this as an integral over eigenvalues. So you have an integral over n eigenvalues and call them m. And you have some van der Waals determinant. So this thing is just a measure. It comes from changing variables from the original matrix integral to the eigenvalue integral. Then that exertion gives this sum over mi. And then there is potential. So far this is true at any n. Now at large n, what you can do is usually do several point analysis. So you exponentiate this van der Waals determinant and basically combine it with this exponential, and then you start several point equation, and you find that there is a competition between the attractive, this potential which tends to clamp the eigenvalues around 0, and this which is like a repulsive force, and you find in the large n limit. I have to go quick over this because I don't have time now, but you can read this in many reviews on matrix models. You find the density of eigenvalues, a continuous density of eigenvalues, say rho x, given by the Wigner semicircle law, which is given by the following form. So rho x, so x represents the eigenvalues in the continuum limit. They distribute in a finite interval between lambda minus lambda. So it's maximum at the origin, and then it goes to 0 at some finite distance. Explicitly, this density is given by this Wigner semicircle law, which in these normalizations exists. Okay. Once you have this density of eigenvalues, you can compute this expectation value easily. Because it goes to an integral over the eigenvalue density to the x, where each of the x, well, this integral with the density of the x is what replaces this sum mi. You plug in that density to this integral. This is just given by 2 over lambda, I1 lambda, where I1 is a modified Bessel function. Okay? So this is an exact result which interpolates between the weak coupling expansion and the strong coupling. now we see here that this behavior is precisely what we expect, because if you remember before, I was telling you that the string tension maps to is proportional to square root lambda. So this exponential behavior to square root lambda is precisely what we expect from something which should go like the exponential of the regularized area of the Wilson loop. Now, what is non-trivial to check is that you get precisely this coefficient in the exponent. You should get 1 times lambda. That can be checked by, I think I'm having a 0. That can be checked by explicitly by finding what is the string solution due to this. If I just can take 2 minutes, I can just write the result. There are many reviews where you can read more details. So let me just write it down without formulas. So we have the circular Wilson loop. 4. What is the worksheet dual to this? It turns out, so I can basically think it as a hemisphere. So it has a circular boundary. It goes at some finite distance in the z direction. Okay. If I denote by r some radial direction on the plane where this circle is, then this worksheet is just given by some simple equation where a is the radius. Of course, since the theory is conformal, nothing in the end depends on that radius, but that's the equation that describes this worksheet. You can check as an exercise that this is a solution of the Euler-Lagrange equations coming from the string sigma model. And what is this this thing? If you choose at about phi, now there will be an angle phi which goes around the circle. So if you call that, if tau and sigma are the worksheet coordinates, phi is tau, you can solve this by saying that r is a over cos sigma and z is a tangent of sigma. And sigma goes from 0 to infinity, where 0 is the boundary of this worksheet and infinity is at that point. Okay? So what is the induced metric of this? The induced worksheet metric, which you can obtain by just starting with the Poincare metric, where this worksheet is embedded and choosing its coordinates. And this is the metric. What is this space? This is just AdS2 in Poincare disk coordinates, or if you want hyperbolic two-dimensional space. So it has the topology of the disk. Boundary is a circle. Sigma going to 0 is the boundary. And what is the area of volume of this space? Well, that has to be regularized because it's nominally infinite due to the fact that this goes all the way to the boundary. But there is a well understood way to regularize the area by subtracting the divergence. And the regularized volume, we can write like this, of AdS2 in Poincare coordinates. Well, there are many ways to get this result. One is just to subtract divergence, another is to compute this volume in dimensional regularization. There are many ways that give the same result. The result is that this is negative. After you regularize it, it's minus 2 pi. And then expectation volume to Wilson loop, which we recorded will be this. That's the area, regularized area of the worksheet. Is indeed so it matches the matrix model. Then one can go further. One can study the fluctuations around this minimal surface and study quantum correction and the string sigma model. Those capture one loop. say one look at higher corrections here. So the one loop part has only been very recently actually reproduced by Zarembo, Fedlin, and Medina, I think. And it does match. These higher loops have never been computed. No, n is
lambda.
Lambda. N is infinite, and lambda can be expanded large lambda. Yeah. So it's alpha prime expansion. Okay. And okay, so maybe this is a good time to stop. So basically, when you do that study fluctuations of this worship, you find some kind of theory for some fields which moves in AdS2, which is this worship, and those fields describe the fluctuations of this. The one loop determinants of those fields give this, but you can study more generally amplitude, scattering amplitudes of those fields in AdS2, and those will be related to correlation functions I was talking about at the beginning, which is what we'll discuss tomorrow. Stop here.
Do you have any questions?
So there are not linear corrections. Is it possible?
Well, so from this you can get, from the matrix model you can get all the Euclidean corrections that you want. It's just Gaussian. So you can solve this exactly. Starts like this. Then there is a 1/n square correction. The query is, let me just try to figure out what it is. It's lambda 48, 2, and so on. Okay. So this should be coming from studying genus 1 worships, which end on that circle. So adding some kind of angles to that. And well, these have never been checked really systematically, but all these Bessel functions that appear at large lambda, they all have the same behavior e to the square root lambda. So it looks like classically adding this angle doesn't do anything to the area, so this should just be some degenerate zero area angles. And the trivial check is probably computing corrections around here. Yeah, we should get like 2 from. But yeah, since this goes like, so you can only detect some difference if you go beyond just the classical area of the worship, apparently. So I'm not sure if there is a proof that the minimal area surface with higher genus are just those with degenerate angles of zero area. But this is what the formula seems to suggest.
More questions? I guess I can speak again.